I'm Ron. I think everybody here knows me, so skip the intro there. This is intended to be a short talk, so I'll be moving through stuff pretty quickly. However, I guess we can expand on anything if people are interested. This is a project where you're setting out to build some sort of custom circuit and attach it to your Raspberry Pi. One of the quickest and easiest ways to communicate with the GPIO header on the Raspberry Pi is the Python language. So we'll get started with just, you have to have some sort of circuit, right? So one tool that I started playing with is called Fritzing. You've probably seen this thing show up in magazine articles. It's kind of an ambitious product that isn't really quite done yet, but it's good enough for small things. You can actually take this through. As you can see here, I have a Raspberry Pi over on the left side here, and I have a 74HC595. It's a TTL chip. It happens to be a shift register with a separate buffer. And this thing over here is it's just an LED strip that has 10 LEDs in it. You got your resistors above to limit the LEDs, and then we have the output of the shift registers are just turning on LEDs. This is obvious. I mean, I guess you could use this as a device. I mean, if you wanted to do like a bar graph or some sort of thing. It's mostly just for demonstration. Interesting thing about this tool is you can actually, once you wire it up that way, you can come in here and draw the schematic. Now, I'll tell you that it didn't come up the first time this way. And I was a little annoyed at the schematic element they have for that bar graph. That looks nothing like a bar graph. But you can get a schematic, and if you really want to push it, you can get a PC board. And supposedly this, again, if it's simple, you can probably send this out to a fabrication house and have it built. So here's the bar graph. Here's the TTL chip. Unfortunately, I didn't realize until I was at this point that this particular part is using the surface mount version of the chip. So this would be, I didn't bother to figure out how to switch that to the dip. With the dip through hole one, but it would be a different PCB layout. So that's an interesting way. This Fritzing program, which you can install for free on most platforms, it does have quite a few components and stuff in it. So there's a lot you can do with it. But at some point, you have to figure out how this chip works. For example. Now, if anybody's into the TTL business or knows about the TTL family, it goes way, way back to the mid 70s, actually. This particular series of TTL, which was invented or brought out by Texas Instrument those decades ago, this has the HC in it, which I believe I read somewhere it stands for high capacity. But this also is a chip that, while most TTL chips need 5 volts to run on, the power, the ground and the power have to be 5 volts. This chip supposedly runs all the way down to 2 volts. You can power this with 2 volts, which leads me to believe it's no longer transistor logic anymore. They probably implemented the whole thing with MOSFETs or something. So we have the circuit. I've captured a schematic, but this doesn't do us a lot of good if we want to experiment with how the chip works. So the next thing that I did is I pulled it up in. I took that, the design, and I put it into something called Tinkercad Circuits, which is an online circuit generation thing that has a simulator built into it. One thing I've noticed with this simulator, it's not very fast. You really have to go slow with it if you want things to keep up. And a couple things we need to know, though. We need to study this chip a little bit. So we'll go grab the. Here's a diagram of what's in the chip, and again, this register has the nice feature that it has a shift register and a separate transfer buffer. And the reason that that's important is so that you can shift data in as a unit and then use the R clock to have it update the output pins. If you didn't have that extra buffer, as you're shifting it in, the pins would change, and that probably isn't what you want to do, especially if you've got them connected to motors and stuff like that.
It's in fact an array of D and RS flip-flops.
Yes, yes.
Yep.
And it's 2 arrays actually. And yeah. So so you have to kind of study this a little bit. You go into the specification, you're going to find timing diagrams. You need to study this to figure out how to drive the thing. Here we have a serial clock, we have the serial data, and we have the R clock, which is the clock that transfers the shift register to the output pins. Now this timing diagram, as far as I can tell, all it's good for is for testing. You would never use it this way. We would more than likely clock in 8 bits of data, and then when you're done with that, then you would sequence the R clock to have it transferred once again, so that your pins on the chip don't change when you're not expecting them to.
Does Tinkercad allow you to pull up data sheets for devices in their library, or you have to go off? I know you're at ti.com.
Yeah, I went off. But I'll show you what it does do in a second. Then the other thing you need to look at, and this is, the electrical parameters of your TTL, and this is all fairly standard. But notice again that this chip goes all the way down to 2 volts.
Oh wow!
Another thing that I noticed about this series of TTL is that the lower voltage also means they run slower. They're not quite as fast. So, but that's that's part of the process you go. Now although I don't believe that I haven't seen anything where you can just click on this and pull up the data sheet, unless it's over here somewhere. But what you can do is you can put your cursor on there and it'll tell you what the pins are. So for example, here's the clear pin, here's the shift clock, the output register clock. And
VCC is probably on the left there, the far left.
Standard TTL dip chip power pins on the corners. Here's VCC and VSS. So there's your circuit. Now I started the simulation. Over here I've got the input just connected to a slider switch. And I've got some LEDs on those 2 clocks. So I can click this. And I found out that I got to hold it for a second, and I just shifted a piece of information in. I'll turn that off and shift in another one, and then I'll turn it on, shift in another one, and we'll shift in another one. Now notice the LEDs didn't change, but now when I hit the transfer clock, there's the pattern 1011. Okay, so that's hardware, and you would spend a lot more time on this than what I'm going over for right here. Well, here's the 595. Yeah, it doesn't seem like there's anything on there as far as data, but the data, we got Google these days, so you can find data sheets on everything, even stuff that hasn't been in print for a long time. So that's the hardware. The next step is we want to do this in Python, so you can go out and study that. Eventually, one of the choices that you'll come across is the gpiozero module, Python module for talking to the GPIO. Apparently, there are 1 or 2 other dominant Python packages, but they're not. They tend, from what I could see, and I didn't look at them that close, they're a bit closer to the hardware, so it means that you have to, you might have to do some more setup. You can't like here in gpiozero, you just declare declare a variable as being an LED on pin 17, you're basically done. Now you can turn it on and turn it off, and you can write. I mean, this is exactly how much code you need to do your first program, and probably get away with less. And you don't have to notice. I didn't have to tell the module how to set up pin 17. It figured it out. There's also the other thing that you find out in GPIO land is there's at least 3 different naming conventions for the pins. It has some way of just realizing that if you put a number in there like that it knows you're using a particular naming pattern. Again, I don't have to specifically tell the module which one of those to use. It figures it out. The only downside to the gpiozero is it may not, because there's a whole bunch of crap going on underneath the hood, may not be the highest performance module. So if you have a performance issue, you might need to look at one of the other libraries that's, again, closer to the hardware. You can see that there's 25 chapters to the GPIO. The documentation is here at gpiozero.readthedocs, and I thought that was just goofy. It's like some website that just collects documentation, but that's actually the home for it, and I'm not sure why. It's not. You'd think it would be. The code itself is up on GitHub somewhere. I don't know why they. Although apparently this is too, but it's rendered nice and pretty as a web page through this site, and this is as far as I can tell, the official site for it. The things you'll be interested in. I mean, you can read through this. There's a good amount of stuff to learn if you want to get into detail. But basically, you're going to look at input devices, output devices, and maybe some of these other ones. The documentation is nice enough to. The thing that I kind of like about it here, we're talking about input devices. It gives you a nice object hierarchy of what what objects are available for doing input devices, like button. A button is you can see the whole family train up to the master GPIO device. They have the similar thing for output. Here's the LED thing that's in the example, and it's it's a subset of digital output device. It actually isn't. It's just a better name for this. They actually, when you go look at the code for it, it's just a big chunk of thing that says pass. It inherits this and then it does a pass. It's just a shorthand for doing LED. Who wants to write all this out when you're trying to just light a LED? So there's some more exotic modules. These are the for different. I forget what these are. These are like different specialty boards, or there could be like Raspberry Pi hats that you can plug in, and people have done libraries for them. Here is the object collection for different. Once you have all the objects that can run the pins, then you can gather up a bunch of pins and put them in like a composite device. All a composite device really is just a collection of pins usually, and then they work in concert as one device, and the composite device will keep them connected. One thing the gpiozero package does is if I allocate a pin, it won't let me do that again until I release that device, which is a good thing. So if you're writing code and you accidentally forget to change the pin number, it'll come back and say you're already using that pin in this context. So again, there's a lot going on under the hood. That's all explained in here in different places. Another thing to look at would be these are the internal devices, and this is stuff that's going on where they can. So this is more like things that are on the Raspberry Pi that you can that's part of the package, and they're just basically front ends for probably front ends for other Python libraries. Another thing that I just noticed today is they have a whole section here on fonts. Now these are, you're probably wondering, why do they got to reinvent fonts? But these are not fonts like your traditional, what you might be aware of. They have a little minimal set of fonts. Like if you're doing an LED array, like a matrix or something, they have the simplistic bit fonts that are like 5 by 7 bits. Just like in the old days on the teletype terminals and stuff. So they're really, really tiny fonts, and they're included so that you can, like I said, drive LED arrays. So I pasted the URL for the document in the chat, so you can grab it there. That's about all we're going to get there from the document. And there's a lot of stuff in there. The other thing I wanted to point out was the nice thing with this way they built this documentation is they got a little link to the source code. So you can read all this, but if you still want to go look at the source code, it'll take you right to it there. So that's kind of a nice feature. All right, so we've looked at we've built some hardware. We've investigated gpiozero. Now we have to start writing some Python code. Well, the first thing you usually do is you probably just sit down and start playing with it, which is what's going on here. And I don't even know if much of this works anymore, but this is just to test the concept. Basically, I need at this point there. One of the bizarre things about the gpiozero things, there's no object for shift registers. So I basically just declared 3 pins, clock, transfer, and data, and set them to the pins 23, 24, and 25. And then I just wrote a couple of real quick and dirty functions that allow you to do stuff with those. And this is how I made sure that my understanding of the chip and the documentation for the chip and how gpiozero works, it was just a place to start. And eventually I realized that when I decided to go back and again look at the gpiozero documentation, I was like, I can't believe there's no shift register. There's no 3-wired shift register. So I decided to make one. And what I wound up doing is, this is on its way to becoming a Python module, and which will probably be an extension to gpiozero. I don't know, I might publish it somewhere. First thing I did was declare a clock pin. Clock pin descends from that digital output device. Here's how you initialize it. That's pretty active. My only difference is a clock pin, it's designed to be pulsed once. So it's not like an LED or a pulse width modulated pin. It's just a strobe it once type of thing. You strobe it. You can set the clock width to 0, in which case it'll run as fast as possible. And I've been running it at 0. If it's at 0, it doesn't do any delay. It only inserts the delay here. And it's been running at 0, and it seems to work okay. Although I don't have an oscilloscope currently, so I can't measure this pulse width, but the chip seems to be able to handle it. So I invented a clock pin. It just has the strobe. I added a strobe behavior. I went and added, did the standard Python thing for adding accessors. Accessors? Like yeah, I think that's what they're called. So you have one this is a reader, this is the setter, and starting to get in the habit of doing that. In this case, nothing's really happening that's special. But the cool thing about the setter is you could put some code in here that would validate the data that you're trying to set it to. So that's a good reason to use it. The other pin that I define as a data pin, and you'll notice I did the same thing they did with the LED. I just descended from digital output device, and all I'm really doing is just giving myself the ability to use an object by a shorter name that makes more sense to this project. Then I created a shift register. This is similar to other composite devices that I went and studied in the gpiozero documentation. And so some things that are just unique to this. So the thing with this, since it's a composite device, it has the mechanism for handling the fact that I'm going to need a clock pin, a transfer pin, and a data pin. And once I give that to this object, it's going to basically go and allocate those, and it's going to manage those. So when all is said and done, and if I want to tear down the shift register, I just call the shutdown on this, and it'll automatically free up those resources. It'll release these devices and free up the resources. That's all happened way up the object tree. Things I defined in the shift register. I just want to know, what direction do you want to shift things in? Most significant bit first, or it's basically it's a Boolean, so it's either this or it's the alternative least first. So I just have it shift MSB first, and that's the default. Also have a chip count in here that I added. So the cool thing that I forgot to mention about the 595 is you can daisy chain these. So if as it is, it's an 8-bit shift register. You want to convert it to a 16-bit, just throw another chip on there. Daisy chain, I think it's pin 9 out of here into the data pin on the next one, and you just copy the clocks all the way down the line. As far as I can tell, it's not a problem whatsoever to like daisy chain like 2 or 8 or 16, and you may even be able to get away with like 32 of them. That would be one heck of a shift register. So the code handles that. You tell it what the chip count is, and that's used for different things. Added since I wanted to minimize the number of pins I was using, there is a reset pin on there, but it turns out it's not. You can effectively implement the exact same thing, but just by shifting in 8 zeros into the chip, and you have a clear function. So then I didn't have to allocate another pin for the chip clear. But here's a clear function. That's exactly what it does. It basically figures out how many bits has to be shifted in by multiplying the chip count by 8, and then calling the clock pin device strobe. Or it puts a 0 on the data pin, and then calls the strobe however many times it needs to get all the bits shifted in. If you only have one chip, it's 8 bits. 2 chips, 16 bits. Here's a send bit function. Basically, it checks to see. You basically give it a piece of data, and it just checks if it's true or false. If it's true, turns the data pin on. If it's false, it also turns it off. You set up the data. You call the clock pin. If on the send bit I have auto transfer set to false, which is a good thing. But if you do happen to set it here, it'll then call the transfer pin. Almost never need to do that, because again, you want to clock your stuff in and then call the transfer device pin strobe once you're done clocking the bits in. Here's the send bits, and this is you can see it here. Here the auto transfer is set to true, because you're going to give it a list. It's going to in the simple case, it'll be a list of 8 elements. If it goes through each element, well, first it checks to make sure it's a list, goes through each element, and then it figures out, it decides which direction you're shifting them in, MSB first or the opposite, calculates the index, pulls out the bit from the list, and sends it to send bit. And then here it says if auto transfer, call the transfer pin. Now, in this case, the default is true. So every time you do this, after it's done clocking 8 times or up to 8 times, then it'll clock the pin that transfers the data from the shift register to the output drivers. I have a send byte. Send byte is able, instead of sending a list as a data pattern, you can send an integer, like a int 8 or a character. There is no character type in Python, so it's a string of 1 is the definition of a character. But at some point in Python, they invented this thing called bytes. It's sort of like poor man's are true arrays. So I added this so that if you send in an object that's of type bytes, it'll deal with that, and as long as it's only got one element or one member to the byte, it'll deal with it. Otherwise, you'll get an error. Stuff there to go through and again properly get everything. So if it's an integer, then you have to use a mask, and you have to roll through the integer with a bit mask and use bit level logic to figure out whether the bit's set, and then you send it to the bit, and then you adjust the mask. In this case, the mask goes up. In this case, the mask goes down. In this case, the mask goes up. That's all it has to do with the shift direction. And again, you have the auto transfer. And then the last thing that I added is send bytes, which would allow you to send a sequence of events. It basically it's like the one above, except instead of sending 8 bits, or instead of sending just 1 byte at a time, you can send multiple bytes, and it'll get them all shifted out. And so the last thing that I need to add, which I haven't got to, is I want the ability down in the gpiozero library. There's this they have objects and modules that will manage threads, and they use a thread like in the LED stuff or the pulse width modulation stuff. You can synthesize pulse width modulation on pins that don't support it in the hardware. And what they do is they start up a thread and let the thread handle the timing on that pin, so that and then you call that, starts a thread, and then it comes back to you, and your program can go off and work on other things. And then when you're done, you got to keep a handle to the thread. But when everything's done, you can pull up the handle for that thread and tell it to stop. The LED in the digital output device, they have a method that will actually pulse, or it'll actually dim the LED by using pulse width, and so that's the way you can do those sort of things. So I could use the same thing. For example, if you were using this to drive some motors or to animate something, then I would want to be able to hand off a list of commands to something and say, I want you to sequence these commands out every second, and then you'd have a mechanism whereby the output bits on the shift register would be going through some like a dance pattern or something, and it could be driving motors or turning lights on or whatever. So that's what I'm looking at next. On this, so this window is actually running on one of my Pis. This is a 3B plus. I brought this window over to my Linux workstation via VNC, so that you guys can see it. On the Pi, I have a camera plugged in, and I have it pointing down to itself and my circuit. And I built this on a breadboard, and it doesn't look anywhere near as pretty as the diagram I showed you. That's because the jumper leads I had were a little bit too long. I have to order some shorter ones. But so one thing I can do here is basically I'm going to run my library to get it to verify there's no bugs in it. Then I'm going to get my test. Here's a test script that basically at the top of it imports the library that I invented, the shift register, and I'll run that, and I'll get the latest stuff loaded in here. And then I have a couple of goofy, like I wrote this, we'll just call this Cylon. Everybody knows what a Cylon is, right?
Remind me.
You might have to remind me.
Yeah.
Me too.
Look at the light pattern. Come on. It'll come to you. Although some of you people might not be old
Is that
enough.
from Babylon 5, maybe?
Close, very close. It's from Battlestar Galactica. So I hope you guys can see the LEDs flashing in the side or the. I'm sorry, that's not the right one. That's not Cylon. That's somebody else. Dang it! What did I do with it?
We do see the LEDs.
Sequencing?
Yes.
Yeah.
Yeah.
See it.
That's
What
cool.
did I do? Oh, I have two versions. I have this one, which I thought was the Cylon pattern. This is the real Cylon. This is the one from Battlestar. Now maybe it'll make more sense. Remember how the LED on the helmets just kind of went. You guys never saw Battlestar Galactica. Oh well.
This is reminding me of Knight Rider a little bit.
Knight Rider is fairly similar. Yeah. Yeah.
It reminds me of my old Bearcat police scanner, except that has rolling zeros across the.
Yeah. So as promised, you have LEDs flashing up in your face, and that's all I got for my short talk. So
Well, thank you, Ron. That was really cool.